Is that a math nerd I see? Coming in to watch some math videos? How dare you? I'm joking, that's me too. You found the right place. All right, so after some pause, we're back at it again with the linear algebra series. And today we're beginning a discussion on one of my favorite topics in linear algebra, which is, drumroll please, eigenvectors and eigenvalues, okay? The reason I like this section so much is that it unravels so many beautiful proofs. And so today I will allow you to begin this journey with me. And again, it is my pleasure that you are joining me on this journey because this is going to be one hell of a ride. So let's get started without further ado. Okay, so what is an eigenvector and what is an eigenvalue? It sounds fancy. Well, I think it's worth starting out with why the heck do we care about these things? Well, first of all, the idea here is that you have some linear transformation, okay? I hope you didn't forget what that was, all right? Please tell me you watched the other videos. Surely. Linear transformation T, okay? All right, let's just say it's from some vector space V to W. And perhaps you're interested in vectors in V that kind of, actually, you know what? We're not looking from V to W, we're looking at operators. So linear maps from V to itself, okay? So in other words, T is how you would usually see this. That is a terrible fancy L. This is supposed to be a fancy looking L, fancy L. Okay, it's seen better days, but it's okay. So it's a linear map from V to itself, okay? And maybe we're curious, what are some vectors and what are some corresponding, what are some vectors so that when T maps that vector and it maps it into V, some element of V, well, that vector stays the same, but it just gets elongated or shortened, okay? All right, I'm just saying words right now, but these words are gonna culminate in something better in a second here. So T, what I'm saying is we're looking for vectors V so that when we apply T to that vector, we get some constant multiple, we're gonna call that lambda. All right, don't get scared away by the fancy Greek letters. Some lambda times V, okay? Now I wanna say, obviously if V is 0, this is true because T of 0, we know T of 0 is 0. That's a property we proved, actually. And so, well, that works for any lambda, actually. So we're going to impose the restriction that we're not looking at the obvious V equals 0. So for V is not equal to 0, we get this, okay? And so that is exactly what an eigenvector and eigenvalue is. The eigenvector here is V. It's this thing so that if you apply T to it, it just elongates or it diminishes. That's not the right word. It elongates or it shrinks in length, okay? So imagine you have, I don't know, we're just looking at R2. It's 2D coordinate system, all right? Okay, and you have some vector here, okay? And let's say we're using some linear map that all it does is, for example, 2i. So the identity map in this case is just 1, 1, 0, 0. In this case, if we multiply by 2, what does this do to things? Well, by the way, I kind of just willy-nilly introduced matrices. Kind of ignore that. But I'm assuming since you're embarking on this journey with me into the land of honors linear algebra, you have some sense of what a matrix is and what it means visually. So you might have heard a matrix is a linear transformation, and it is indeed a linear map. In fact, all linear maps can be expressed as matrices. And I kind of evaded that topic in linear algebra done right. You know, Axler wouldn't be too happy, but that is sort of a stale topic in my opinion. So I think I would argue it's enough to have just a sort of a basic understanding of what a matrix is. But I will actually, you know what, I will create a supplemental matrix video just for you guys. All right, for the love of the game. So just let me know if you want access to that. I'm not going to post it. Again, it feels a little stale. This is the good stuff here. All right, I just wanted to get to the fun stuff. Okay, So the identity map, let's express it as a linear map itself. Okay. Of course, this is the identity matrix, but equivalently, we can write. Let's write the identity map. Let's call it. I is usually how you would denote a matrix. So let's use lowercase I. There's probably a better way. I'm just sort of blanking out. Let's just call it, I don't know. Let's call it, yeah, lowercase I. Oh, that really bothers me. That's buns. But it's okay. So lowercase I of xy just sends xy to xy. But we've multiplied it by 2. So in this case, our new function, our new linear map is t equals 2 times xy. So what is that doing to each vector? Well, all it's doing is stretching it by 2. So this vector in this coordinate system then gets mapped by t. This is indeed an operator. It's operating from R2 still to R2. This vector here, let's call that b, gets sent to 2b. It's just stretched by 2. So what does that mean? That means every vector here is an eigenvector under this specific linear map, okay? Because this linear map quite literally doubles each vector. That's your lambda, that's your v, okay? Every vector then in R2, besides of course the origin, because we're not counting 0, is an eigenvector, and it has corresponding eigenvalue, what? Well, just 2, right? And why the heck do we care about this? Well, it has plenty of applications, okay, for you applied mathy people. I'm one of them. So this is also coming from personal experience because I love them eigenvectors. But just to name a few, if you've ever heard of this concept in data analysis called principal component analysis, PCA, it takes a bunch of data, okay? This is not the greatest example because I don't have, believe it or not, an 1,000-dimensional brain. But usually when you take data, okay, so for example, if I'm trying to understand the trends in the grades, the grade point averages of students in Houston, Texas, my hometown, my beloved Houston. If you're looking at the GPAs in various schools, okay, you're going to be tracking various features, okay? If you've ever done artificial intelligence, you'll know what I'm talking about exactly. In order to get an understanding of the actual GPAs, that's your output, you're looking at things that might affect that, all right? Maybe some sort of demographic values, perhaps some sort of metrics for the academic proficiency of that school, I don't know. Okay, the location, okay? All of these different factors, that's a ton of dimensions, all right? If you're taking all these data points, each one corresponds to an axis, okay? Obviously, I'm simplifying it here, okay? This is just 2 dimensions. But the point is you get all of these complicated features and you want to simplify that. You want to make some kind of order out of this madness, all right? And so that's where PCA comes in, okay? It simplifies that for you because it looks for the trends in the data. So if I was looking at this looks like a whole load of nonsense, but I'm noticing a lot of variation occurs in this direction, and a lot of variation occurs in that direction. So what principal component analysis does is it looks at the covariance matrix, so the way sort of this data is varying in a probabilistic sense, okay? And then it extracts sort of the biggest changes in that data. Okay, in this case, that would be sort of these axes. This is where the data changes the most. And it does that by computing the eigenvectors and corresponding eigenvalues. Okay, and then using those principal component vectors, all right, you can extract those and then say something meaningful about the data. Okay, so that's that. That's very, very useful. Very, very applicable in many situations. In fact, there are these things called eigenfaces. And so I'm going to try to draw it, but sort of there was this massive data set of faces, okay, and some research group, okay, sort of ran PCA on this massive data set of faces, and PCA in turn outputted a bunch of a bunch of these PCA vectors, these eigenvectors, sort of in order of how much variance versus, less variance, these kinds of things. And it gave you these silhouettes of faces that kind of represented a human face the most. And it was interesting because you kind of see a human face, but it's like some weird amalgamation of all these faces. And it's like, it extracts features that most represent us, like a nose, you see some structure of our eyes, ears, these kinds of things. So this is what that's good for. Well, what else is there? I'll name one more, just to not waste your time too much. We have, in physics, for all my physics nerds out there, sort of rigid body rotation. So if you're looking at a satellite or any sort of thing that's moving through the air, you want to just understand, like, what are the axes that we can sacrifice it to rotate around when torque is applied to it. Like if you have friction, it's applying some kind of torque. Air friction, it's applying some kind of torque on, some flying body. You want to understand which axes it's most stable on. And so that involves this thing called an inertia tensor. It's like a tensor is sort of like a multi-dimensional matrix, okay? Three-dimensional matrix, for example. It's like you have a matrix, but then you have like some depth to that matrix. It's kind of cool. I can go over that later on too. But what you can do is, well, if you think about eigenvectors, there's some kind of stability there, right? Because you're looking at vectors that when you apply some kind of rotation matrix to it, not necessarily rotation matrix, but some kind of, it's almost like that. Then they stay fixed, so you can find your axes of rotation by looking at which vectors stay fixed under some kind of transformation when you represent, when you're trying to model, torque applied onto some flying object. So this is really useful for dealing with stability in a system, okay? Okay, enough applied math. Where are we at? We're at 12 minutes. So I think in the next video, we're gonna get right into the math of it. And now that we've sort of developed some justification of why the heck you might care about eigenvalues and eigenvectors. So I'll see you then. Toodaloo.